Okay, so we're going to look at section 11.2, which is on what's called a series, which is basically the next step from looking at a sequence. Okay, a sequence is a list of numbers. A series is when we add up a list of numbers. Okay, this is the notation that we used when we talked about a sequence. Okay, generally, we name a sequence with a lowercase letter. And then the n stands for the particular term you're looking for. So for example, if you wanted to know the third term in sequence A, you'd plug 3 in for n and do it up. Right. What we're going to look at, something a little different. We're going to look at some sums. Okay? Sum means to add up. And the notation I'm going to use is a capital S, lower subscript n. What we're going to try to find is the sum of the first n terms in this sequence. Right? So let's list out some of the terms in the sequence just so we can see them, and I think that'll make more sense. So the first term, I'm going to fill in 1 for n. What's 2 times 1? 2 minus 1? Square. Okay. Oh. Yeah, we don't have to do that. Next term. Yep, and before you write it as 9, how did you get 9? Yeah, 3 squared. I think if I leave it as squared, you're going to see a pattern. Okay, next term.
5 squared.
5 squared. Yeah, and we're going to stop there. But the pattern here is basically you're squaring odd numbers. Okay. And again, we can do those out, but for now we don't need to. All right, so if I wanted to find what's called S sub 1, that means in this sequence that I have, I want you to add up the first 1 terms. So if you add up the first 1 terms, what term are you adding up? Yeah, just you're adding up 1 squared. Okay. What about if you wanted to find S sub 2?
1 squared plus 3 squared.
Hey, you're adding up the first 2 terms. 1 squared plus 3 squared. We'll do one more. How about S sub 3?
1 squared plus 3 squared plus 5 squared.
1 squared plus 3 squared plus 5 squared. And lastly, if we were going to do S sub n, you're adding up 1 squared plus 3 squared, plus 5 squared, plus 7 squared, however high you're going to go. And what is your last term you're adding up? It's the nth term. So you would just fill in n for you're plugging into, and it's 2n minus 1 squared. That's the nth term. But the important thing to understand in this section is n is finite. Okay? N is definitely a number. Could be 20, 50, a million. The point is, there is a highest value you stop at. We're not going to infinity. So, any questions on this notation? All right, so eventually what we're going to try to do is, let's figure out what these are. What's 1 squared? And then 1 squared plus 3 squared? 10. And then 10 plus 5 squared? And then, well, let's do one more. S sub 4 would be 1 squared plus 3 squared plus 5 squared plus 7 squared. So 49 plus 35. 84. Okay, and now what we just created here is basically another sequence, okay, where each term in this sequence is a sum. The sum of the first term, the sum of the first 2, sum of the first 3, sum of the first 4. And we're going to try to find a pattern in this sequence. Okay? And I'll tell you what the name of this sequence is in a second. Okay? Each individual S sub n, S sub 1, S sub 2, S sub 3, S sub 4, those are all what we call a finite series. Okay? Does finite means it goes on forever, or there's an end? Yeah, there's an end. Okay? So each one of those is called a finite series. because there were a certain number of terms we added up. Sometimes we just added up the first 2 terms. Sometimes it was the first 3. Sometimes it was the first 4. But the point is, it was finite. There was a certain number of terms we added up. Right? Now, suppose we created a sequence out of S sub 1, S sub 2, and S sub 3, and so on. This, what I just wrote right here, S sub 1, comma, S sub 2, that's called a sequence of partial sums. If you want an example, 1, 10, 35, 84. That's a sequence of partial sums for the sequence A sub n that we had earlier. And the goal is, if you can find a pattern in the sequence of partial sums, then you can add up as many terms as you want without doing it by hand. Okay. Right now, if I asked you to find S sub 50, well, in this formula, unless you see a pattern, you would have to find all 50 terms and then add them up. Okay. By the end of today, I'm going to show you a way to get the answer without finding all 50 terms. There's a way you can do it. So, any questions on what a sequence of partial sums is? Just a sequence where each number is the sum of all the terms in a sequence, up to that number you're looking for. Okay, so generically, S sub 1 is the first term. S sub 2 is the first 2 terms in your sequence. S sub 3, sum of the first 3. S sub n, sum of the first n terms. Right, so just how we pronounce it, this is called your first partial sum, second partial sum, third partial sum. How would you pronounce this one? Yeah, it's your nth partial sum. Okay, any questions on partial sums so far? All right, so next thing we're going to look at is a kind of a compact way of writing a sum using a Greek letter. And it's going to give us a very, very quick way instead of having to write out things like this. And it's called sigma notation. Okay, so sigma notation, it's just a short way of writing down something when you want to add up a bunch of terms. Right, so let me show you how you would add up all the terms, starting at the first term, going to the nth term. First thing you have to do is write your capital sigma symbol. On the bottom, we write k equals 1. The letter you use can change. It depends on what they give you. But the 1 basically means you're starting at the first term. And the n means you're ending at the nth term. And then a sub k is the sequence of numbers that you're going to be adding up. So I'll just show you an example of what a real problem would look like, and then I'm going to come back to it. So you don't have to write down this problem yet, because we're going to do it. But in this sequence, I'm asking you to expand it by adding up all numbers from 1 to n, and that's the sequence you're going to plug into. So k starts at 1, and then it goes to 2, it goes to 3. You never use decimals. Okay, this number always represents a term, okay, in a sequence. And the way you pronounce it is the sum from k equals 1 to n of the sequence a sub k. Okay, the number on the bottom has a special name that's called your index. And the letter can vary. Okay. Generally, whatever the letter they use in the sequence, that's the letter they use for the index. Those letters have to be the same. Okay, how do you pronounce what's on the left-hand side? That's a capital S and a subscript 5. Yep.
The fifth partial sum.
Yep, this is the fifth partial sum. And now on the right, how would you pronounce it? Just plugging in what I have here in that notation. Go, Corey?
Be the sum from k equals 1 to
5, yep.
of 2k plus 3.
Of the sequence 2k plus 3, yep. And let me just show you how you do that out. If I actually wanted you to evaluate it, you just plug in every number from 1 to 5 going by integers in for k and add them up. So start with 1. 2 times 1 gives me 2 plus 3. 5, yep. Now go to the next number, k equals 2. 2 times 2, 4 plus 3, 7. Next number is 3. Andrew, what's 2 times 3?
6.
Plus 3? 9. And then the next one's going to be plus 11. And the last number you're going to stop at is when k is 5. Okay, this is the stopping point. 2 times 5 is 10 plus 3, 13. And we could go ahead and add all those up. You'd get 45 if you add them up. But in this case, I'm just showing you how to expand something in sigma notation. Okay, questions on that? All right. So when you write it with the Greek letter and you have your index, your stopping point, and then your sequence, that's sigma notation. When you write it the way I just showed you right here, that's called expanded notation. That's when you actually write out all the terms. Okay, any questions on the difference between sigma notation and expanded notation? So if you see the directions in the book or on the test, expand the following sum, I'd like you to do what we just did on the last problem. Just do it out. All right, let's try this one. What's different about expanding this sum versus this sum?
The previous one actually has a definitive stopping point.
Right. So the first one, we knew the stopping point. This one has a stopping point. It's at n. We don't know what n is. Okay, but n is not infinity. It stops somewhere. So what would the first term be? If 2 plus 3 is 5? Yeah, just leave it as 5 squared. That's fine. If you leave it as 5 squared, I think you'll see a pattern. Okay. Now, after k equals 1, then we go to k equals 2. 2 times 2?
4.
Plus 3? 7. Let's do one more. 9 squared. So basically, it's the sum of odd numbers squared starting with 5. Now, it goes all the way to the nth term. So what we're going to do now is do plus, put in dot, dot, dot. After you've shown me the first 3, I can see you know the pattern. And now go all the way to the nth term. What would the nth term be?
2n plus 3 squared.
Yep. You plug in the last number. 2n plus 3 squared. And there's no dot, dot, dot after 2n plus 3. That is the end of the sequence, of the series. Okay, so that's what I'd be looking for to ask you to expand that. Questions on that? All right. Another thing I want you to see is, look at the index. What has our index been for every problem? It's been 1. Okay, it doesn't always have to be 1. Okay, let me show you. This is called re-indexing, changing the index. Let's say you had something like this. I want to add up from 1 to 5. I'm adding up multiples of 2. Basically, I'm adding up 2, 4, 6, 8, 10. Right, so the first term, you plug in 1. 2 times 1 is 2. Second term?
4.
Yep, plug in 2 for k, 2 times 2 is 4, and so on until you get to the last term, 5. 2 times 5, 10. Okay, let me show you another way you can write that. That's the same thing. I'm going to go from k equals, well, I could do 4, but I'm going to do from k equals 0 to 4 of 2 k plus 1. Okay, watch what happens here. If you plug in 0 for k, what's 0 plus 1? Times 2?
2.
First term is 2. Now the next one, k equals 1. 1 plus 1? 2 times 2?
4.
4. So we're getting the same terms we did. Your last one is when k is 4. What's 4 plus 1?
5.
Times 2? 10. So these are exactly the same thing. Okay? Basically, the point is, if you subtract 1, you have to do it to the top and the bottom. You can make those 1 smaller. And then you have to adjust your k in your sequence to be 1 bigger to keep it balanced. Right? So if you started this off at like -1, I'd have to end at 3, and I'd have to put in a k plus 2. And that would be another way to write the same summation. So any question on reindexing? Just in case you see something like that on a test, like if you get an answer like this, and I have the answer on a test like that, just know that they're the same thing. Okay? All right. Next thing we're going to look at is some properties of summations. And these properties are going to allow us to combine things and split things apart that have summation symbols. Okay, here's the first one, and I think the easiest thing to do is to just make up an example and show you how it works. You can almost kind of think of it as like distributive property with sigma. They don't really call it distributive property, but you could kind of think of it that way. And let me show you a simple example. Let A sub k be very, very short sequence 1, 3, 5. Let B sub k be another very short sequence, 2, 4, 6. I'm just going to show you with these two sequences that this formula works. Okay, on the left, what it's saying to do first is add up all the terms in my sequence and then add up the results. All right, so let me show you what A sub k plus B sub k is. Okay, let's just do that part first. Add up the terms in the corresponding positions. What's 1 plus 2? 3? 3 plus 4? 7? And 5 plus 6. That's the sequence A sub k plus B sub k. Just add up corresponding terms. Now, I'm going to add up all of that. Okay, so now I'll show you the sum of A sub k plus B sub k. What's 3 plus 7?
10.
Plus 11?
20.
21. So doing it the way on the left, you get 21. Okay, let's look at the way on the right. It says first add up everything in A sub k. Okay. So what's 1 plus 3 plus 5?
9.
9. Plus, now add everything in B sub k.
12.
12. And what's 9 plus 12?
21.
Same thing. Okay. So that's what that rule says. It's two different ways to add up two sequences. Either add up the terms first and then add up all those results, or add up everything in the first sequence, everything in the second sequence, and then add those results. Same thing. If it works for addition, what else do you think it works for?
Subtraction.
Yep. So really, if you wanted to write it as one rule, you could just put plus or minus signs. Plus or minus, plus or minus. Basically the same rule. Okay, I'm not going to go through an example with that because it's so similar. Let's look at the last rule, which basically says if you want to multiply a sequence by a constant, you can either multiply each term in the sequence by the constant first and then add the results, or add the results, and then multiply that sum by the constant. Comes out the same either way. And this one I'll show you with an example. A sub k was the sequence 1, 3, 5. Let's let c equal 2. I can pick any constant I want. Okay, c stands for constant. It's just a number. All right. What's c times a sub k? If I distribute my constant to each number in that sequence. 2? Yep. 6? 10. That's c a sub k. And now I'm going to find the sum of c a sub k. I'm just going to add them all up. In this case, I only have 3 terms to add. What's 2 plus 6 plus 10? 18. Okay, that's doing it by multiplying each term by the constant first and then adding them up. Let's try it on the right. First, let's find the sum from k equals 1 to n, actually 1 to 3, of a sub k. What's the sum of the first 3 terms in sequence a sub k? 9. And now let's find 2 times that sum. K equals 1 to 3. That's going to be 2 times 9, which is how much? 18. Did we get the same thing? Yeah. Get the same thing either way. So when you have a constant multiplied by a sequence, you can move the constant in front of the summation. Any questions on that third rule? How did I get 2? Oh, I just made what's in the box would be given to you. But it works with any constant. You can take the constant, put it in front. Good question though. Any other questions? All right, so now what we're going to try to do is use these 3 rules to either take 2 separate sums and combine them, and we'll do it the other way in a little bit. Take a combined sum and split it. Notice whether you're combining or splitting, what happens to the index and the number on top? Stays the same. So if I want to write this as a single sum, where's my index going to start?
1.
Yep, k equals 1. And where's it going to stop? N. And now basically, to add these up, just pretend that this is sequence a sub k, and this is a sub k. So you don't have actual numbers, but you do have like terms. So what would the k squared term be? 6k squared. How about the k term?
2k.
Negative 2k. And what about my constant? 3. That's it. We just combined 2 separate sums into a single sum. In that case, we used rule 1 kind of in reverse. We went from right to left. Questions on that? All right. So writing things with sigma notation is nice, but it doesn't actually help you to do anything faster. Okay? If I wanted to know what this is the sum of the first 10 integers. 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9 plus 10. That's what this represents. If I wanted to do that out, I have a short way of writing it in sigma notation, but I would still have to do every one of those out and add them up. This does not give me a fast way to calculate anything. It just gives me a fast way of writing what I want to calculate. But you still have to do it by hand. So I'm going to show you a couple shortcuts that can speed this up, at least in certain cases. So we're going to first look at something even a little simpler than that. Okay, I want you to look at something like this. I want to add up from k equals 1 to 5, and the formula for my sequence is 4. Okay. When I plug in k equals 1 to my sequence, what's my first term? 4. When I plug in k equals 2 to my sequence, what's my second term? And when I plug in k equals 3? And how about when k equals 4 and 5?
4.
It's 4. So all you're doing in this case is you're adding up a constant. So what's the answer? Or what are you really doing here? If you wanted to write this shorter. Yeah, all you're doing is 4 times 5. 4 times 5. So if I wrote something like this, you're adding up a constant, whatever the constant is, n times. What do you think the formula would be? Yeah, Cn. So now this gives you a quick way, if you're adding up a constant n times, to do it. The formula is C times n. Okay, I'm going to show you a couple things. I'm going to show you a quick way to add up a constant, to add up just integers, like 1 plus 2 plus 3 plus 4, to add up squares, 1 squared plus 2 squared plus 3 squared, and so on, and cubes. Okay, 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed. We can come up with as many formulas as you want, but these are the only ones you're responsible for. All right. Let's take a look at this one. So this is now taking it one step further. We're not adding up a constant, but we're adding up the first n integers. Okay, so what would be the sum of the first 1 integers? 1. What's the sum of the first 2 integers? 3. How about the sum of the first 3 integers?
6.
Yep, 1 plus 2 plus 3 is 6. How about the first 4 integers? First 5? And the first 6? Yeah. Now if I said, how about the sum of the first 4,000? Yeah. Okay. So now we got to come up with a method. We don't want to literally add up every number from 1 to 4,000. Okay. I'm going to show you a trick at how you can figure out this pattern, but I'm not going to go through this trick every time. Okay. Take your numbers, write them like this. And what we're going to find is a difference tree. Okay. Anyone ever done this before? What's 3 minus 1? And 6 minus 3? 10 minus 6? 5? 6. Do it again. What's 3 minus 2? 4 minus 3? You get all ones.
Do it again.
No, we're done. Thanks. But I'm all set. Now, how many times did we have to do that process before we got a row that was the same? Twice. What that means is this pattern, anybody know? There's a 2 involved somewhere, but it's not multiplying. It's a little more complicated than that.
It's
Squared. It's going to be a quadratic pattern. Okay, the previous pattern was linear. Okay, a number times n. This is going to have n squared. Okay, if you ever did something like this and you're not sure what the pattern is, Your calculator can help you figure it out. You go to Stat and Edit. Type in all these as coordinates. Type in 1, 2, 3, 4. You don't even need this many. You could do it with less. Okay, we've got 1, 3, 6, 10, 15, and 21. So what the calculator is going to try to do is, well, I have to tell it what to do. Right, what kind of pattern did we say this one was going to be?
Quadratic.
Quadratic. So I'm going to go to Stat, I'm going to go to Calc, and I'm going to tell the calculator to look for a quadratic pattern. Okay? So I have to know what kind of pattern to look for. I put my x's in L1 and my y's in L2. So I don't need to change anything. And it tells me the formula is 1/2, I'm going to use n as my variable, 1/2 n squared plus 1/2 n. There's a different way that we normally write it. If you did this out, what's n times n? N squared. And n times 1? N. And you're dividing each one by 2. This is the same thing. Okay? Take half of n squared, take half of n. But that's the pattern if you want to add up the first n integers. Let's try it. Let's add up the first 5. What's 5 times 1? I'm sorry, 5 plus 1? 6 times 5. Divide by 2. 15. Okay. So this is a nice, simple formula. So now if I said add up the first 4,000 integers, simple. 4,001 times 4,000, divide by 2. Tells you what the answer is. Choose your calculator. Okay. Any questions on that pattern? Okay, the other patterns, we could go through the same way. If you made a difference tree using perfect squares, anybody have a guess how many times you'd have to do it before you get a row of constants? Yep, you'd have to do it 3 times because it ends up being a cubic pattern. Now you might look at it and say, well, wait, there's no n cubed. If you FOILed it out, there would be. We give you an n squared, and then if you multiplied that times the other one, you'd have an n cubed. How about the next one? It's not going to be an n cubed. What do you think this one will be? Yep, this is a quartic pattern. And if you did out the distributive property with the parentheses, you'd have an n squared, and then you distribute your n squared, you'd end up with n to the 4th. Right, so basically what these formulas allow you to do is take something that has a summation in it and get rid of the summation. Okay? When we're trying to find formulas, we generally don't like summations in the problem. If we can, we want to substitute in a formula to replace the summation. But keep in mind, all of these formulas are from k equals 1 to n. So you have to be given a problem with that index and that upper bound. Does everyone have the formulas? Let me leave all of them up if I can. All right, so now we're going to try to come up with a formula for this. Again, let's say I asked you to add up the first 200 terms in this pattern. You don't want to have to find all 200 terms. There's got to be a way to just find the answer without finding any of the terms. And there is. We're going to use these formulas. But the first thing I have to do is split this apart into 2 summations, 1 to n and 1 to n. What do you think I'm going to put as the argument for my first summation? Negative 2k. And how about my second? 3. Now, the second summation we could do right now. I showed you one just like that earlier. It's from 1 to n of a constant. Okay, so that one we could do. But the second one, I need to have just a k. Does anyone remember what I'm allowed to do with a number? Yep, you can move it right to the front of that sequence. So we're going to have negative 2 from k equals 1 to n of k plus the sum from k equals 1 to n of 3. Now I'm going to use substitution to replace that. I'm going to find the formula for it, and I'm going to replace that. Find the formula for that one. Generally on the test, I probably wouldn't give you a cubic one, because the algebra, it's going to take a long time to do out. But anything squared and lower, you could say. So what am I going to write in place of the sum from k equals 1 to n of k? N times n plus 1 over 2. Yep. And what am I going to write in place of the sum from k equals 1 to n of 3? 3n. Yep. And now once we simplify that, that's our answer. Right. Before I do this, anything I can cancel out? Yep. Can cancel those. So now I need to distribute a negative n. What's negative n times n? What's negative n times 1? Negative n. Plus, what do I still have on the end?
3n.
3n. So what's my final answer? Perfect. That's a formula to find the nth partial sum. So now if I said to you, add up the first 200 terms, simple. 200 squared, make it negative, plus 2 times 200. That's what it would add up to. Any questions on that? Okay, without doing those substitutions for sigma, you're stuck doing the whole thing out, all 200 terms, and adding them up. Right? Now you got rid of the sigmas.
So how did you know to use the n plus 1 and 2?
Because I look k equals 1 to n of k, and then I looked right here. The sum from k equals 1 to n of k is n times n plus 1 over 2.
Okay.
So and then for the other one, it was k equals 1 to n of 3. That's this top one. K equals 1 to n. Just replace c with 3. 3n. Okay, let's try one more of those, except this time we're not going to do out all the algebra. Let's at least get to the step where we substitute. How many summations is this one going to be broken into? 3. They're all going to be from what to what?
K plus 1.
2? Good. Okay, and then I'm going to have plus another k equals 1 to n, and then a minus k equals 1 to n. Anyone think they can tell me what the first summation will look like?
2 on the left.
2 on the left,
K squared on
k squared on the right. Good. How about the second summation?
the 5 on the left. K on the right.
5 and k. And how about somebody else, my last summation?
2 on the right.
Just 2 on the right. Now, someone in the last class said, could you have done a plus and a negative 2? Sure. It's the same thing. Whether you add a negative or subtract a positive, it's the same thing. And now tell me what I would be substituting for. I'll circle what I'm going to substitute. Just the k?
K squared and the whole thing besides
The whole summation for the k squared. The whole summation for the k, not 5.
the last one away
Just that 2 is missing.
So what should I circle here? The whole thing, except the minus. So the last one, what would this simplify to? Yeah, that would be 2n. This one would be 5 times, actually let me write it. This one would be 5 times what?
And plus 1
Over 2. And now the first one we haven't used yet, k squared. That's n plus 1, 2n plus 1 over 6. So now the algebra is going to get a little messy. Not awful, but you do have to distribute some things out. So n plus 1, 2n plus 1, all over 6. And there was a 2 in front. Plus. So that says 2n, n plus 1, 2n plus 1. And if I had to do it out, I would just distribute and go from there. Combine like terms. But I'm going to stop with that. So any questions on converting something with sigma notation into something without sigma? All right. And the last thing. So we're going to look at finding a formula to add up a finite number of terms in a geometric sequence. Right. So now I could say, here's a geometric sequence. Tell me what the first 35 terms would add up to. Okay? You're going to be able to find the answer without finding any of the terms. You're just going to be able to find the answer. All right, so let's look at our geometric sequence. Okay. What's the first term I wrote in this geometric sequence? Yep, a sub 1. And remember, in a geometric sequence, are you multiplying or adding? Multiplying, right? Adding is arithmetic. And we're multiplying by what each time? R. So take your first term, multiply it by r, that's your second term. Take your second term, multiply it by r again, and that's your third term. Multiply by r again, and what would the fourth term be? A1r cubed. The next one, you'd multiply it by r again, a1r to the fourth, and so on. Notice, if you look at your term position, if you look at your term position and you look at your exponent, it's always 1 less. Second position has an exponent of 1 on the r. Third position, exponent of 2. Nth position, 1 less than n minus 1. Right. Now, I want to write down the nth partial sum. Okay, so I want to add up all the terms from the first term to the nth term. Okay. What's my first term?
Wait, no. A sub 1.
A sub 1. What's my second term? A sub 1r. What's my third term?
A sub 1r squared.
Yep, let's write one more. What's my fourth term?
A sub r cubed.
A sub 1r cubed. And now there's going to be a bunch of terms. Maybe we add up the 5th, the 6th, the 7th, the 8th, the 9th. And now finally we're at the nth term. What's my nth term?
A sub 1r minus 1.
Yep, a sub 1r, the n minus 1. Good. Now, I'm not going to do anything very complicated. All I'm going to do is take what I just had up above and multiply everything by r. And I'm going to write it again. Okay, so what do I get if I multiply the first term by r?
A sub 1r.
Yep, now I get a sub 1r. How about the second term?
A sub 1r squared.
A sub 1r squared. Okay, how about the third term?
A sub 1r cubed.
Now it would become a sub 1r cubed. Plus,
A sub 1r.
so you'd have, yeah, a sub 1r to the 4th, to the 5th, to the 6th, to the 7th, a bunch of terms in the dot, dot, dot. And then, what would my last term be? A sub 1r to the n. Somebody tell me what the term would be just before that one?
A sub 1r n minus 1.
Yep. That would be the one just before it. And the one before that would be a sub 1r to the n minus 2, and the one before that, r to the n minus 3. Now, the way we're going to get our formula for the sum of a finite geometric series, I want to subtract these two things. Take the top one minus the bottom one. Now, the first thing I want to look for, does the top one and the bottom one have any terms in common? Yeah, it has a ton of terms in common. What happens when you subtract things that are the same? They cancel out. So look at the top one, look at the bottom one, and tell me terms they have in common. A sub 1i. I agree. If you subtract, those would cancel out. What else?
A sub 1r squared.
Yep, that would cancel out.
A sub r cubed.
A sub 1r cubed would cancel out.
And a sub 1r minus 1.
Right? All the dot dot dots would cancel out with those dot dot dots. A sub 1 r to the n minus 1 would also cancel out. So what are you left with in the top?
A sub 1.
A sub 1r to the n.
All you're left with in the top is, yep, a sub 1. All you're left with in the bottom is minus a sub 1 r to the n minus 1. Those are the only two things that didn't cancel out. And now my goal is to get s sub n by itself. When I'm done, I want something like this. I want s sub n equals, and then I want a formula. So anybody see what I can do on the left-hand side?
Can you just add r as
Well, if I added that, then it would move the s sub n to the other side. I like the idea that the s sub n's are at least on the left.
Divided by negative r.
No, not divided by negative r.
How about just regular r?
Think about when you have the same thing in two spots. What can you do with it? Okay, if we had like terms, we could combine them. Or what if I said to do something with this?
Square root.
I'll take x out.
You could factor out something they both have in common, in this case, like an x. So what do these both have in common?
A1.
Sine.
S sub n.
That's
Negative 1 minus r.
So what are you left with?
A
1 minus 1.
Yep.
1 minus r.
Now we only have s sub n in one spot. Keep the other side the same. And now, how would you get s sub n by itself?
Subtract 1 minus r.
Divide by 1.
Yeah, remember that's multiply. Divide by 1 minus r. Divide by 1 minus r. And there is our formula. I wouldn't even figure out this trick, okay, without having looked it up. But that's the trick with how they come up with the sum of a finite geometric series. Okay, and it works. So we get a sub 1 minus a sub 1 r, which actually we can do the same trick we just did a second ago. What does the numerator have in common?
A1.
Yeah, so we could pull out the a sub 1. And what would you be left with in the top?
Negative 1 minus r.
1 minus r over.
1 minus 1.
And there's your formula for the sum, nth partial sum, of a finite geometric sequence. So now if I said to you, find the sum of the first 200 terms, all you have to do is let n be 200 and type it in. You don't actually have to find any of the terms except one of them. What's the only term you need to know? You've got to have the first term. Okay. Right, so in addition to the first term, you need to know r, which is your common ratio, and you need to know what partial sum you're looking for. I'll tell you what partial sum I want you to find. Okay, so in this problem, I'd like you to find the 12th partial sum. So what letter is going to be equal to 12? N. How about a sub 1?
2.
Yep, a sub 1 is 2. What other letter do I need?
R.
And what are you multiplying by each time?
2/3.
1/3.
1/3.
1/3. It's like you're dividing by 3 each time, but you don't want to think of it as division. Think of it as what did you multiply by.
Okay.
1/3. Now just fill into your formula. So the 12th partial sum is going to be 2 times 1 minus 1/3 to the 12th divided by 1 minus 1/3. Let's see what we get.
Wait, how do you get NS 12?
Because they told me to find the 12th partial sum. All right. 1/3 to the 12th power. What kind of number is that going to be? Really small. It's a third times a third times a third times a third 12 times. It's pretty small. So when I do 1 minus 1/3 to the 12th, I'm going to be subtracting an extremely small number. So what am I going to get here, you think? Something very close to, yeah, very close to 1, just a little smaller. 0.999998. Now, the next thing I'm going to do is divide that by, what's 1 minus 1/3? So I'm just going to do that part. Let's do it like this. Divide by 2/3. And the last thing I need to do, I can't forget. Yeah, I had that 2 on the outside. So if I add up the first 12 terms in this geometric sequence, I get 2.999994. So this might give you a hint if you were to add up infinitely many terms. What do you think the answer would approach? It does. It approaches 3. And it approaches very quickly. If you just add up the first 12, you're extremely close to 3 already. Never mind if you add up the first 500. Okay. If you tried this with something much bigger than like 30 or 40 as an exponent, I don't think you'd have enough decimals. The calculator would just say 3. Okay. So any questions on finding the nth partial sum of a finite geometric sequence?
So you shouldn't round the numbers that you get?
Yeah, I'd probably ask you to find like the 5th or 6th partial sum. So I'd probably want you to write out at least 3 or 4 decimals. Yeah. So you'd probably have like 2.999, and then it'd be a different number. Okay. Other questions on that? Another thing you could try on the calculator is type this in and let that be a variable. Let that be x. And then you could use your table in the calculator to look at the 12th partial sum, the 13th, the 14th. You could look at any of them. Just let that be a variable. And then you could look at the picture and see how quickly the curve approaches 3. Okay? That's the approach we're going to take when we look at an infinite series tomorrow. Okay, homework tonight's on 601, and it's 1 through 17 all.